Every time you swipe a card, refresh a feed, or load a web page, you generate data. We produce quintillions of bytes of it every single day, flooding into servers at blinding speeds. But in its raw, unorganized form, this information is unstructured noise. It is essentially locked inside a vault with no index and no way to read it. To extract actionable knowledge from this chaos, engineers have to build specialized architectural systems designed to capture and serve that data exactly when it's needed. For decades, the relational database was the standard. You built strict tables, linked them with defined relationships, and required every piece of incoming data to fit that exact blueprint. These systems were designed for ACID compliance, providing absolute consistency on a single machine. But that model hit a wall when web traffic required data to be distributed across hundreds of servers simultaneously. The overhead of maintaining those rigid table joins across a global network made the old architecture a bottleneck. Modern database engineering responded by splitting into two categories: systems optimized for high-structured reporting and systems built for high-velocity scale. Choosing the wrong structural category for a task can lead to system crashes or leave critical business insights buried under layers of slow queries. The data warehouse is the ultimate structured vault. It's an integrated repository designed to be subject-oriented, pulling messy data from different sources and standardizing it into a unified history. This diagram shows a star schema, the blueprint for data warehouses. It centers on a fact table, holding quantitative data, like sales or inventory. Surrounding it are dimension tables, providing textual context, like city or product name. This layout prioritizes fast reading over writing. This rigid architecture is brilliant for analyzing corporate history, but it requires constant maintenance. If a source system changes even one field, the entire transformation pipeline can fail. To interact with that warehouse data, analysts use OLAP, Online Analytical Processing. OLAP takes a flat data grid and folds it into a multidimensional cube. These cubes pre-calculate every possible data intersection. When asked a complex question, the engine doesn't perform new math. It instantly retrieves the answer from a specific coordinate inside the cube. The trade-off is latency. Calculating these cubes takes hours, and if the data is sparse, these arrays waste significant storage space on empty cells. Because of that pre-calculation lag and the heavy processing load, this structure is insufficient for handling the millisecond-fast, unpredictable writes of a global web application. That led to the NoSQL movement. These systems toss out rigid tables and fixed schemas to prioritize flexibility and continuous availability. Document-oriented databases encapsulate all related information into a single, human-readable JSON format. Instead of joining 5 tables to find a customer's address, the database fetches one document that contains everything. Column-oriented architectures take a different path. By grouping data by columns instead of rows, they can compress massive datasets and easily ingest high-velocity streaming data from IoT sensors with minimal disk activity. Key value stores are even simpler. They act like a dictionary, retrieving unindexed data blobs tied to a unique name. This is how websites handle millions of user sessions without slowing down. Their core advantage is horizontal scalability. As shown in this diagram, these systems partition their data and distribute them across a cluster of commodity servers. NoSQL trades absolute, immediate consistency for the ability to scale across a masterless, peer-to-peer network without a single point of failure. Modern organizations don't choose just one side. They bridge the gap using a hybrid knowledge discovery pipeline. Think of it as a funnel. NoSQL captures the chaotic, high-speed data on the front end. That information is then cleaned, transformed, and moved into a rigid data warehouse on the back end for long-term trends. Once that data is categorized, engineers run data mining. These are mathematical engines that scan the records to find hidden patterns or anomalies. But these insights are only as good as the structure beneath them. Identifying the right structural category is the prerequisite for turning raw bytes into human knowledge. We see this in predictive mining, where models study historical patterns to forecast outcomes. This is how banks evaluate millions of transactions in seconds to identify and block fraudulent purchases. We also see it in descriptive mining, which groups unlabeled data into clusters. In healthcare, this allows researchers to discover hidden patient profiles and develop more effective diagnosis paths. Managing the modern data explosion isn't about finding one perfect database. It's about knowing exactly when to enforce rigid structural rules and when to break them for the sake of scale.